This lesson is on Lewis structures. We're continuing from yesterday. Before we take a look at Lewis structures, we're going to look at the relationship between bond type and bond order. Then we'll look at the relationship between bond type and group number, then the relationship between bond type and bond length, and then the relationship between bond type and bond energy. Then we'll take a look at Lewis structures for ions. So if you don't have one out already, I would suggest that you pause the video and get a periodic table. All right, so we're going to start out with bond type and bond order. So our bond types are single, double, and triple. So we'll start out with a single bond. And we know that a single bond consists of two shared electrons or one shared pair of electrons. So we can represent it with two dots for two electrons, or we can represent our single bond by a dash. And when we have a single bond, we say that the bond order is 1. We have one pair of shared electrons. All right, we can have a double bond. And we learned that a double bond consists of two shared pairs or 4 electrons between the two atoms. Or we can write our double bond as 2 dashes. And the bond order is 2. It's that easy. And then our last type of bond is a triple bond, which is 3 shared pairs or a total of 6 electrons. And we can represent that as 3 dashes, and our bond order is 3. So bond order is as easy as that. Single is 1, a double bond is a 2, and a triple bond is a 3. Okay, so now we're going to look at the relationship between the bond type and the group number. So this is why it is good to have your periodic table. All right. So we're going to start out with looking at group 17, and we're going to include hydrogen. So group 17, the next to the last group on the periodic table, they are the halogens. So for group 17, they have 7 valence electrons. So if we look at fluorine, fluorine has 7 valence electrons. It's a halogen. And if we look at hydrogen, hydrogen only has 1 valence electron. So now, fluorine has 7. Fluorine wants to get the octet, so it's only going to share this 1 electron with an atom that's also going to share 1 electron. So since fluorine only has this 1 open spot, as does hydrogen, hydrogen is only going to share up to 2 because that will fill the first main energy level. So hydrogen is only going to share, it can only share its 1 electron, and it also wants to share only 1 electron. So group 17 and hydrogen, they're only going to make single bonds. Single bonds. They're not going to make doubles or triples. And if we look at the Lewis structure of HF, hydrogen shares its 1, fluorine shares 1 of its 7, but now hydrogen has the duet. We'll call that a duet because it's got 2 electrons, counting the shared electrons. Fluorine has a total of 8, including the shared electrons, so fluorine has the octet, and that is a good Lewis structure. So our halogens, fluorine, chlorine, bromine, iodine, they're only going to make single bonds when we do Lewis structures. All right, let's look at group 16, and we are considering the nonmetals. As we said that for covalent bonds, we usually have nonmetals in our bonds. So group 16, so we have oxygen, sulfur, selenium. We're going to kind of cut that off at the staircase. So for group 16 nonmetals, they will make single or double bonds. They can either make 2 single bonds or 1 double bond. So if we take a look at oxygen, oxygen's in group 16, so it has 6 valence electrons. So it's got 2 spots where it can make a bond. So it can share this electron with some atom that has an electron to share and make a single bond here, or it can do the same over here. So we have water as an example of that. And here oxygen is sharing with hydrogen and sharing with this hydrogen, and it's making 2 single bonds. And we've also seen that oxygen can bond with itself like this. And here we have a double bond between the oxygens. So group 16, single or double. And we're talking about the nonmetals. And then we have groups 15 and 14. So these guys can do it all. They can make single, double, or triple bonds. And that's all there is. We don't go above triple, single, double, or triple. And we're going to take a look at carbon, some compounds containing carbon. Carbon in group 14 has 4 valence electrons. But first for group 15, an example, nitrogen with its 5 valence electrons. It's got 3 spots. It can make 3 singles. It could make a double and a single, or it could make a triple. And then carbon, and other nonmetals in group 14, they can make 4 single bonds. They can make 2 doubles. They can make a triple and a single. So there's 4 spots here to make bonds, but we only go up to triple. All right, so now we're going to take a look at some compounds containing carbon, and we're going to make a nice chart. So we need 4 columns in our chart. So we'll start out with the name. So the compounds that we're going to look at, their names are ethane, ethene, and ethine. So they are 3 different compounds containing carbon. When we see this prefix F, this means there are 2 carbons. Ane means all single bonds, and these compounds are hydrocarbons. They only have carbon and hydrogen in them. So we're going to take a look at the Lewis structure for each one of these. So ethane has a single bond between 2 carbons, and it's a hydrocarbon. Carbon has 4 valence electrons, so 1 is in this single bond, and it's going to make single bonds with hydrogens. So it looks like that. There is our Lewis structure, no lone pairs anywhere. All right, ethene also has 2 carbons, but the ENE means that there is a double bond between the carbons. So carbon has 4 valence electrons, so it has 1 electron there, 1 electron there. Then it's going to use 1 electron to make a bond with hydrogen, and its other electron to make a bond with hydrogen. Same with this carbon. It's got an electron here, electron there in the double bond, and then it's got 2 more valence electrons that it's going to use to bond with hydrogen. And then we have ethyne, and no surprise here, we're going to have a triple bond between our carbons. So each carbon puts 3 electrons into the double bond. It has 1 electron left that it uses to bond with a hydrogen. So these 3 molecules are hydrocarbons. And we talked about them briefly when we did balancing equations. Hydrocarbons are compounds containing hydrogen and carbon, and there's lots and lots and lots and lots of hydrocarbons. They're important as fuels. Or Bunsen burner gas, methane gas, is also a hydrocarbon. All right, so now let's write the formula for each of these hydrocarbons. So we just count up the atoms in our molecule. So we have C2 and 1, 2, 3, 4, 5, 6, H6 for ethane. For ethene, we have 2 carbons and 4 hydrogens. And for ethyne, we have 2 carbons and 2 hydrogens. Okay, so now we're going to look at the carbon-carbon bond type. So the C-C bond type. That's what we're interested in each of these. So of course we have a single bond in ethane. We have a double bond in ethene and a triple bond between the carbons in ethyne. So then we can easily write our bond order. We just learned that, but that's super easy. The bond order of a single bond is 1, the bond order of a double bond is 2, and the bond order of a triple bond is 3. All right, so far so good. And now we're going to look at the bond length between the carbon-carbon bond. Okay, so bond length. And the unit for that is PM for picometers. So that's a very small length. And I'm going to give you some data here. And of course, you don't have to know these numbers. We're just going to be looking at the trend. So for ethane, the carbon-carbon bond length is 154. Here it is 134. And here it is 120. And remember that the bond length is the distance between the nucleus of one carbon to the nucleus of the other carbon. And then lastly, we're going to look at the bond energy. And our units here are kJ, that stands for kilojoules, it's a unit of energy, which we don't have to worry about, per mole. All right, and the numbers here are 346, 6, 12, and 835. Okay, so what I would like you to do now is to look at the data and make some statements about the relationship between the bond type and the bond length, and between the bond type and the bond energy. So I encourage you to pause the video, write a sentence, and then come back and we'll see how you did. So go ahead, pause the video. All right, so what scientists do is they collect data and they try to look at the data and analyze it and see if they can come up with trends. So if we look at this from the bond length, we can see that going from a single to a double to a triple, the bond length goes down, it decreases, the bond length gets shorter. And if we look at our bond energy, going from a single to a double to a triple, the bond energy goes up. The bond energy is the energy required to break the bonds. When you have a bond and you want to split it up, split those carbons up, you have to put energy in. So it takes more energy to break up the carbon-carbon triple bond than it does to break up the carbon-carbon single bond. So to put that in a sentence, and you could have different sentences, but one way to straight the trend is as the bond order increases, the bond get shorter and stronger. So as we go from single to double to triple, the bond length goes down, the distance between the nuclei goes down, and the energy required to break the bond goes up. Our bonds get stronger. Now, to make this comparison, we have to have the same atoms on either side of the bond, but we could say this trend for a nitrogen-oxygen single bond or a nitrogen-oxygen double bond. So we would say that this bond here is longer, and this bond of the two is the shorter, and this bond here is the weaker of the two. Takes less energy to break this one, and this is the stronger of the two. So the same trend that we saw between two carbon atoms, we see in nitrogen-oxygen bonds. All right, so now we're going to move on to ions. So we've talked a little bit about ions, and there are different types of ions. The ions that we've talked about so far when we did ionic bonding are monatomic ions. A monatomic ion is a single atom with a charge. Ions are not neutral, they have a charge, and they can be positive or negative. So for example, we can have the sodium ion, Na+. Sodium is in group 1, it has one valence electron. It loses that electron when it becomes an ion, and it has a positive charge. We can have Ca2+. Calcium has two valence electrons, it's a metal. When it loses those two electrons, it becomes 2 positive. And then we can have our negative ions. We can have Cl minus, N3 minus. So our metals lose electrons, become positive. Our nonmetals gain electrons and become negative. Chlorine has 7, it gains 1 to become chloride. Nitrogen has 5 valence electrons, it gains 3 to become nitride. So let's take chlorine, for example. So if we look at chlorine versus chloride, in terms of their electron dot structures, so chlorine is in group 17. It has 7 valence electrons. The chloride ion, it has 7, it gains 1 to get the octet. So the chloride ion then has an electron dot structure that looks like this. And to show we have an ion, we usually put them in brackets and put the charge on the outside. So our chloride ion has the octet, but our chlorine ion does not. It only has 7 valence electrons. All right, we also have what are called polyatomic ions. A polyatomic ion is a group of covalently bonded atoms with a charge. So here this is like monoatomic, mono meaning one atom. Here poly meaning many, or at least more than one atom. So this is a group of covalently bonded atoms with a charge. Because whatever type of ion you are, you have to have a charge. And the whole group acts as a unit. So the group acts as a unit. So when ionic compounds are made, the whole polyatomic ion group acts just like a single ion does. So examples of polyatomic ions, and they can be positive or negative, most are negative. You can have NH4 with a +1 charge, and sometimes you'll see it written like this, and sometimes you'll see it with parentheses. We can have SO4 with a 2 minus charge. And another example, NO3 with a -1 charge. And now we're going to learn how to do Lewis structures for polyatomic ions. It'll be very similar to how we learned to do Lewis structures yesterday. The only difference is we're going to have to account for the charge in terms of the valence electrons for when we do our structures. Okay, so let's do NH4 plus first. Okay, so we're going to do a valence electron count as normal. So nitrogen we have 1 and hydrogen we have 4. Nitrogen in group 15 has 5 valence electrons for a total of 5 valence electrons. Hydrogen has 1 valence electron. So 4 times 1, we have 4 valence electrons for a total of 9 valence electrons. Now we have to look at this charge. What does it mean to have a positive charge? It means that you have lost an electron. It means that this group lost a valence electron. You lose 1 negative, you become 1 positive. So of these 9 valence electrons, 1 electron is lost for the charge. This is for the positive charge. We have to take away electrons. So we end up with a total of 8 valence electrons. This is the number of electrons that we use for our Lewis structure. So we put in our nitrogen, put our hydrogens around the nitrogen, and put in our 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. And each hydrogen now is sharing 2. It's got the duet. Hydrogen's done. It's satisfied. Nitrogen has 2, 4, 6, 8 around it. Nitrogen has the octet. So that's good. The only thing that we add to show an ion is we use brackets. And then we put the charge as a superscript outside the bracket. So that is the complete Lewis structure for NH4+. And the name of this is, the ion has a name. This is called the ammonium ion, NH4+. We're going to see that again. All right, so let's do another one. We're going to do OH minus, and the name of this is the hydroxide ion. So, well, even though it only has 2 atoms, it's still polyatomic. Anything more than 1 is a polyatomic ion. So we do our valence electron count. Oxygen, we have 1. Hydrogen, we have 1. Oxygen in group 16, so 6 valence electrons. And hydrogen, only 1 valence electron. So we have a total of 7 valence electrons. Now we have to look at the charge. Minus, this is -1. It's minus because the group gained 1 electron. So we add 1 electron, 1 valence electron for the negative charge. So we have a total of 8 valence electrons for our ion. So we have oxygen, We have hydrogen, put in our 8 valence electrons. 5, 6, 7, 8. Hydrogen is 2, it's good. Oxygen is 8, it's good. Just put in our brackets and the charge outside of the brackets, and we're done. Okay, let's try another one of these. Let's do SO4, 2 minus. This is the oops, I forgot the L, the sulfate. Oh, I gotta write that over. It's the sulfate ion. That's the name of it. Okay, so we're gonna do our valence electron count. So sulfur, we have 1. Oxygen, we have 4. Sulfur in group 16, so 6 valence electrons. And oxygen is also in group 16 with 6 valence electrons. So we have a total of 6 times 4, 24 valence electrons. We add them up. 6 and 4 is 10, carrier 1. We have 30 valence electrons. Again, we have to consider the charge. 2 minus means the group gained 2 electrons. So plus 2 valence electrons for the 2 minus charge, giving us a total of 32 valence electrons. Okay, so we put sulfur, put those oxygens around it, and we're just going to put everything in, put those 32 electrons in evenly, and see what we come up with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I'm out of electrons. Now I have to check all my atoms. For the octet, oxygen has it, oxygen has it, oxygen has it, oxygen has it, sulfur has it. I'm good, all single bonds. The only thing left to do, put in my brackets and put a charge of 2 minus outside of the brackets. All right, let's do one more. And this one is NO3 minus. This is called the nitrate ion. So let's do our valence electron count. 1 nitrogen, 3 oxygens, nitrogen in group 15 with 5 valence electrons, oxygen in group 16 with 6 valence electrons. 6 times 3 is 18 valence electrons. We add them up. 5 and 8 is 13, carrier 1. We have 23 valence electrons. And then we look at our charge. -1 means the group gained 1 electron. So plus 1 valence electron for the minus charge. So we have a total of 24 valence electrons. All right, nitrogen in the middle, 3 oxygens around it. It doesn't matter if you put the oxygen there, it doesn't matter where you put them. All right, let's put in our 24 valence electrons, just put them evenly and see how we do. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And if you put your electrons in different spots, it won't matter. You'll still end up with the same Lewis structure if you do moving your electrons correctly. So we put in our 24, that's all we have. We can't add more. And then we look, and nitrogen in the middle has 2, 4, 6. It only has 6 valence electrons. The oxygens, they're all okay with the octet. So we got to move some electrons to give this nitrogen an octet. So we can take these two and bring them in. And it wouldn't matter, you could take these two, you could take those two, that doesn't matter. And when you do that, then you get a double bond, and then this oxygen still has its lone pairs of electrons. Here we have a single to the oxygen, and then here we have a single to the oxygen. And now nitrogen is 2, 4, 6, 8. All the oxygens are good. We just put in our brackets and do that minus sign outside of the brackets for the charge. Whoops, I went off of the page there. So that's what our correct Lewis structure looks like. And it doesn't matter if you have the double bond here and the two singles here, or if you have the double here and the two singles there. That doesn't matter, but you just need to end up with one double and two single bonds. All right, that's it.